Welcome, everyone, to the Oxford seminar. This week, we're hearing from Khyathi again, who's telling us about the Mandela effect, misinformation, and conspiracies in quantum categories.
Thank you for the introduction. Basically, I just want to motivate a lot of the quantum computation and category theory related stuff that I've been thinking about for about a week now. Uh, just using some other social phenomenon that I've also been thinking about. Just to give, wait, why? Okay. Just to give a rundown of exactly what I'll be talking about and what to expect from this talk. So basically, I've been thinking about how classical memory is very different from human memory. So, if, for example, you note things down in a notebook, you can like go back to the page of the notebook that you noted something down and you can read it. And then you're like, oh, yeah, I remember this, that I noted that down at that time. And you're not going to forget something that you wrote down in the notebook because you can always go back to the notebook and retrieve that information. Whereas human memory is far more complex because let's say, for example, you don't remember something that happened to you when you were 3 years old or 4 years old because it happened a long time before. That's just very different. Basically, I'll just be talking about how classical memory works, how misinformation can be modeled in these quantum categories, the Mandela effect, and yeah, just basically talk about all of this stuff in the quantum computation perspective. Anyway, so these are two pictures of the Starbucks logo, and I want you to tell me which one you think is the actual Starbucks logo, the one on the left or the one on the right.
They wouldn't put a star in it. Yeah, that's in the name.
So thank you so much, because you are wrong. It is the one on the right. And this is a famous example of the Mandela effect, where we misremember things, we misremember logos and a lot of different things. So this is exactly the sort of phenomenon that I want to be talking about and sort of formalizing in this talk. Yeah. So like I said before, let's say that you note something down in your computer or in a notebook. The order that you write things down in your notebook or your computer doesn't matter because you can revisit it at any point of time. Whereas in the human memory, your order does matter. So some psychological experiments where we understand that order does matter is Loftus's leading questions, where basically he showed human beings like this video with a bunch of car crashes and things like that. And he asked these questions where he made it seem like he was deciding a certain answer, but actually he was tricking the person into believing that there was something in the video that actually did not happen. And these people would basically just like misremember things that actually did not happen in these videos. And there's also this research by Schumann and Kressel, which shows that the order in which you ask people questions really changes the answers that they give to questions. And Ebbinghaus also noticed that if you give people a list of items to remember, they tend to remember the things that are in the beginning or at the end and sort of completely forget what's in the middle. So really the puzzle is, how do we model human beliefs and human memory when it's so complex and like it sort of doesn't commute, right? Because something that you remember in like that happened to you before, you don't remember in the same capacity as something more recent. So how do all of these like things just come together is really what we're trying to model here. So I will be modeling Mandela effects using this category of completely positive maps on a finite dimensional Hilbert space. I'll be modeling misinformation using the concept of a mixed state and how you can have many purifications for it that are not necessarily unique, and how you will be modeling conspiracy theories using this local coherence versus failed global glue. So basically, stories that seem that they're locally correct but may have contradictions when considered in the big picture of what really is happening. So I'll start by talking about the Mandela effect. And I have three examples of the Mandela effect that I'm going to show you to really just show you what sort of different ways the Mandela effect does happen. So first, these are two logos. One is spelled Bernstein Bears and the other is spelled Bernstein Bears. Which one do you think is correct or has the correct spelling? The one on the left or the one on the right? I did not either. I thought it was just me.
Probably the one on the right, because that looks the most wrong. Left. I know how trick questions well.
Congrats. So Tim is right. It is the Bernstein Bears. So the reason this happens is sort of semantic. We see a lot of people's names and we're sort of biased into believing that their name should end with Stein rather than Stain, because that's just the pattern that we see around us. So it sort of has to do with the order that we are exposed to names that end with Stein before being asked this particular question. If perhaps you did not know that there are names ending with Stein, you might be able to like identify it correctly. So this is an example of like the semantic order confusion Mandela effect. Which Pikachu do you think is the correct Pikachu?
Like whether or not it's male or female changes the.
No, that's
the
Pikachu versus Pikachu, I think. Yes.
The one on the left.
It is indeed the one on the left, but people here are just too smart for this. It's not my fault. It's just that you understand three questions. It's
Every
not.
night before goes, I would look at the 121 original Pokemon and like memorize them and believe the names.
Wait, that's for real. Yeah, so most people would say that is the one on the right because they sort of see it as like picture of Pikachu and they see that, oh, like most of his ends have black on it, so perhaps also the tail does have black on the end and they think it's the one on the right. So this is an example of what we call schema reconstruction, where we see this pattern and our brain sort of just auto-completes that pattern without giving it much thought, and we just assume that it should have a black tail when it does not. So it's the final example of the Mandela effect that I'm going to show you. So this is the Monopoly Man. Hopefully everyone here has played Monopoly. Okay, so there's one on the left and one on the right. Which Monopoly Man do you think is the actual logo?
All right.
Because
think it's the left.
anyway, so most people do think that is the one with a monocle, mostly because we see a lot of imagery of wealthy people wearing monocles, and we have this social bias that, oh, it should be. And there's like a lot of other cartoon characters at the same time that Monopoly came out, which were like these wealthy characters who had an animated monocle on them. So everyone just sort of just like confused that with the Monopoly Man and thought that the Monopoly Man should also have a monocle. So that's where that came from. So now we see three different kinds of Mandela effects and exactly what sort of thing that tells us about our memory. So the first one, the Bernstein and Bernstein one, really tells us about the order in which information is shown to us. The second one, which is schema reconstruction, tells us about how our brain just tends to like complete patterns. And the third one, which is the source, sort of tells us how our biases and like these different informations that we have about wealthy people and our idea of the world sort of just pushes us toward a certain thing. So using these examples that I gave you, if you think about memory, it's sort of just like re-encoding all of the information you have. You probably get a lot of unbiased data from the world, but the way you perceive it or your beliefs about it are sort of biased by your internal worldview and things like that. So that's really what we are trying to like model here. So the math behind this is I'm going to be telling you about completely positive maps, a little bit about what I know about quantum, and why I think that this quantum computation model could perhaps be a nice way to model this stuff. But yeah. So the way memory works is that this is just like four examples of registers for memory. So what I mean by registers here is really like things that impact our memory or our worldview later on. So that's the actual source that we have, the context we have behind this, the visual memory that we have, and the semantic memory. So basically, we will be modeling how memory registers work using finite dimensional Hilbert spaces. I will give a reason for that in a bit. And this category of finite dimensional Hilbert spaces is something known as a dagger compact category, which I shall also define. And in the next few slides, basically, you might be wondering why do we have to do something that's so complicated to model this? And that's basically the question that I'm going to be answering. So what is the category of finite dimensional Hilbert spaces? So the way to think about it is that Hilbert spaces are basically these vector spaces where like all of the mad part of quantum occurs. So it has a specific kind of inner product that allows us to like quantum operations and things. So the objects in this category are finite dimensional Hilbert spaces. The morphisms are linear maps between them. And the reason we chose Hilbert spaces is because this sort of inner product structure that we have allows us to like compare different states. So like how similar memories are or how different memories are. The orthonormal basis basically helps us model these like pure memories that we have, like for example, if you're told like maybe the alphabet for some people, this is an oversimplified model for what it's worth, but yeah, so basically the orthonormal basis is perhaps can be your worldview or something like that, basically the way in which you see things. And the tensor product is a way of combining registers into one joint system. So one of the main reasons that we will be using the finite dimensional Hilbert space category to be modeling this is because it is what is known to be a dagger compact category. So this dagger is sort of this operation that you have on this category, and this is an involutive conservariant endofunctor. So this gives us a way to sort of reverse update. So sometimes we believe something and then we get some new information that sort of results in us like not believing that anymore. So in a sense, our beliefs are sort of reversible. So I think the dagger structure could perhaps help us model that. In a compact closed category, we have caps, which here in this specific case correspond to evaluation morphisms, and cups, which correspond to co-evaluation morphisms. So graphically, this means that if you were to draw diagrams, string diagrams for this by any chance, you can basically bend the wires up and down, and that could possibly just like help you better understand this graphically. But yeah,
Wait, sorry, one time, why are you allowed to, why are you, you can't copy a qubit, you can't like copy data, that's not allowed.
wait, what do you mean?
Like, there's a no clone theorem for qubits, right? Like, you can't.
This is not cube. This is like spaces of like.
Oh, sorry, these
yeah,
are
these
just
are
Hilbert
Hilbert.
spaces.
Yeah, yeah,
Oh,
Hilbert spaces.
sorry, okay,
Yeah.
yeah, no, cool. I'm so happy.
You scared me for a second.
Sorry. You scared me.
Anyway, so we have like this complete string diagram calculus. So an oversimplified way to understand this is really that the wires that go inside and come outside the boxes sort of represent your inputs and outputs, which here these spaces are meant to like represent the registers for your memory, or like what sort of stuff just affects your memory. So that's the input and the output. Whereas the boxes themselves sort of represent the updates or the processes and what really these registers do to your memory. And the bending could either like be some sort of forgetting or just like reevaluating stuff that you have thought of and things like that. But yeah. Anyway, so I wish that we could just use the category of finite dimensional Hilbert spaces. But as you can see, the morphisms here are linear maps, and that's just not good enough for us. And the thing that we want to model is quite complex. And still, when we make it more complicated, it's insufficient. And I'll get to that in a little bit. But yeah, so basically I will tell you exactly what morphism choice we will be using and why. Yeah, so in this category of finite dimensional Hilbert spaces, it's very hard to model this thing called a mixed state. So we have these state spaces in this finite dimensional Hilbert space, and it mostly just corresponds to pure states. And we can't really model these mixed states, which is like a mix of the quantum data and the classical data, which sort of corresponds to human belief systems. It's like it's a mix of truth and also a mix of a bunch of biases and a lot of false data and things like this. So we really want to be able to model mixed states. And updates aren't all unitary, which means that these like linear maps between these finite dimensional Hilbert spaces are probably just insufficient to model what we're trying to like do. So instead, we will be using this thing called a completely positive map. So a completely positive map, I'm just type checking this now, I'll give a proper definition of it later on, is basically a map that goes from A star tensor A to B star tensor B. So if you have like you can like construct this like completely positive map category on these like Hilbert space categories. So in the case of the finite dimensional Hilbert spaces, you have the exact same objects which are finite dimensional Hilbert spaces, but instead of linear maps being the morphisms, you now have completely positive, in this case trace preserving, but they don't need to be maps, and they are closed under the composition and the tensor product, and it's still a dagger compact category like before because of that. So here's an example of a positive map. So here F is a positive map. It's the composition of G and G dagger. G dagger is the convolutive invariant endofunctor that I defined earlier. So this is what a positive map is. So diagrammatically, this is what a completely positive map is. I'll give you a while to look at the diagram. But basically what it's trying to do is just sort of give you some extra conditions on how the duals work and how they can be manipulated more diagrammatically. Or at least that is what is more relevant to things in GX calculus. So yeah, that is what that is. But
So this is a complete bottom map from A,
A tensor A star to B tensor B star.
right, is this, I can't really see where that's happening. So like, is this, where is the data of such a map being presented in?
This perhaps was not the best diagram to use.
Like that
The morphisms.
that composite is a CP, like both of those left and right hand sides are a map.
So,
Yeah, like the leftmost thing and the rightmost thing.
And we would call either of them a completely positive map from A to B.
from A to B,
From A to B. So like the type checking for the morphisms is A tensor A star to B tensor B star, because that's the type that the density matrices are in. But the actual objects of the category are A, B, and it has all the duals in the same category. But yeah.
Does F contain G and
It's
G
close.
star?
What?
Does F contain G and G star?
F is a map.
It's a map.
Yeah, it's like a map between finite dimensional Hilbert spaces.
like there's arrows pointing in and out of the top and bottom, like, sorry, where did F come from?
Because you can compare F is defined to be like a G tensor G dagger.
Yeah.
That's it.
From before.
So we start with a linear map, G.
Yeah.
Yeah.
And we compose it with its transpose,
Conjugate transpose.
and that's just gonna give us an ordinary map from A to A, right?
What's an ordinary map?
A linear map.
Oh, okay. Oh.
I mean,
We could pause on this. Or
Yeah, okay, we can-
For example, here's another definition that doesn't use ZX calculus or string diagrams or anything.
Mhm.
A positive map is one that is positive. Like it has nice things to provide in vectors. A completely positive one is that one that remains positive whenever you tensor it with any identity. There's like a linear.
right, but that sounds like a condition rather than the extra data of.
Yeah, it's not. It's
It
just
does
like
sound like that, doesn't it?
Okay, we can
Yeah, that's an interesting
It's-
point.
think about this more later.
You can get these guys from a model
no,
structure.
it's mostly that we want them to be of the type A dual tensor A.
Mm.
And like,
Yes.
yeah, it's based more of a type checking thing, which hopefully will be more clear in the future. But if not, I'm happy to talk.
Okay.
Right. Anyway, so yeah, you might wonder exactly why this is a good choice, which is what I hope to motivate later on, which is now. Anyway, so why CPM? So now you notice that the domain and the codomain are sort of this form of like B star tensor B. So density matrices, which are what model these mixed states that I was talking about before, they are of the form CX tensor CX dual. So if you notice, that's very similar to like the B star tensor B stuff that we have, because the objects at the end of the day here are finite dimensional Hilbert spaces. So we have the same type now. So it's sort of this type checking problem that we are trying to solve. And because density matrices now model mixed states, we now have a way to talk about mixed states using the category that we have. Whereas if we just had FT Hilbert, it would just be pure states. So that's what we are trying to model.
Okay, sorry, density matrices are of that form, is that just saying X is some set or something and this is, well.
Yeah.
Okay,
A density matrix is not a priori defined as a matrix.
okay, it is just like a linear.
It is actually a matrix.
Okay. Okay, sorry.
That's all right. Yeah, so I just want to like clarify exactly what is what in this quantum setting really. So a belief here is like the state of a register. So the registers here are the finite dimensional Hilbert spaces, and the belief is the state of that register. So a register is like, imagine you have X and then there's an operation that happens on X. And after that, what is the state of X? So after the operations are done, what the final state is, that is what a state is. So a belief is basically defined to be what happens after all of the updates, after all of the information, at least at that specific time point at which you're considering. the beliefs. So that's like the final thing is the belief. And the update is basically like the operation that's happening on this register or on the beliefs. So yeah, it's the influence that's applied on the register. So recall is often sequential. So like one of the main differences that I said between classical memory and human memory is that the order doesn't matter so much in classical memory as much as it does in human memory. So I'm going to demonstrate that by mathematically modeling the Bernstein-Bears example for you using the setting that I have and sort of prove my point, sort of, and the limitations of this model. So fun fact for you in the middle as a break from the math. There are 2 countries in the world that have spread so and so memes for from like government agencies of those countries so that people would believe the meme instead of what is factually correct. So they spread the memes before the news became like actual news so that people would believe the memes rather than the news. So this is an example of how like the order of exposure sort of matters. So when people like actually came to know about the news, they would not believe it because they thought the meme was the right thing. So yeah, that's an example of what I'm going to be talking about next. Anyway, so now that I define what it is like more verbally, I just want to talk about where these states of beliefs and like how this like modeling of a meme or fact really lives mathematically. So the state of a belief is sort of like this density operator that you have on the register. So it goes from I star tensor I, which is basically I, to A star tensor A. The reason I wrote I star tensor I is just for the type checking thing, because CPMs are of the form A star tensor A to B star tensor B.
Sorry, I is the terminal.
Yeah.
Okay.
And the channel is basically like this sort of completely positive map that goes between these Hilbert spaces. So it's a completely positive map of the form A star tensor A to B star tensor B. And sequential updates are basically shown by competition. So let's say that you have a channel that's acting on the state. It gives us some sort of influence on the state. And then there may be like under channel that adds more influence. So you can like sort of compose these channels is the idea that's going on here. But we also have this other issue that sometimes we just forget things. Like maybe you are like exposed to both fake news and actual news at once. And you forget the fact that one news was fake, or you forget some details of like what you learned. So we need to be able to model this as well. So the one thing about quantum is that we are able to model information loss. So perhaps that's another reason to be using this as well. So the way to do this is that Kocher and Abramsky, I hope I'm pronouncing that right, have this notion of an internal trace. So the internal trace has a discarding effect and this mixed state effect. So what that does is basically you take a mixed state and you go to the terminal object, or you can start from the terminal object and get a mixed state. So it's sort of like the beliefs that you have can either be forgotten or you can just get like a completely new belief out of nowhere. So that's what the trace allows us to do. So this definition of a trace, this is basically the definition of the internal trace, the trace that they have. And this definition of a trace is very important to us because if you notice, C is sort of in the definition, but in the final map, there's no C. So you notice that C sort of like plays this implicit role in the definition, but at the end, when you're like considering the trace map, C is nowhere to be found. So C plays a role, but it's sort of forgotten. So the intuition is sort of that you inject this neutral object in a sense C, and then it's sort of completely discarded at the end when the map is defined. So if you have any F that goes from A tensor C star, tensor A tensor C to B tensor C star, tensor B tensor C, then yeah, this is how the trace is defined. And you can sort of just like get rid of the C. So yeah, you sort of, our brain has this tendency to sort of just like remember what we find interesting and sort of completely forget where we got the information from. So yeah, that's sort of an issue that we have. And C is basically meant to model for us how we forget sources of information, but rather just remember what we want to remember. Yeah. So now I just want to give an example of a working example of how this works. So we have a channel that like corresponds to meme and another one that corresponds to fact. So let's say that acts on A, which is given by V tensor S, let's consider V to be like a visual space or S to be like a semantic space, and A is sort of a tensor of them like together, and we have like channels acting on this. So the way we define channels is using this thing called a Kraus operator. I won't get too much into detail as to exactly what a Kraus operator is doing. That's a discussion I'm happy to have later on. But a Kraus operator basically just like it acts on this space of density matrices that you have, and it's defined in such a way as like the first thing that I wrote. So like you have Ki and Ki dagger, and it keeps on like acting on this entire space of density matrices that you have. So the purpose of cross operators in this particular scenario is that let's say you have two cross operators, one that sort of biases you toward a meme update, and the second one that sort of corrects you to like the fact. So these cross operators can sort of like encode your bias or a lean toward a certain thing being true. So both these cross operators are completely can be modeled as completely positive maps. So these are non-commuting as well, which sort of supports the thing that we are trying to model anyway. Yeah, so the point of cross operators is to evaluate the effect of the quantum operation on a density matrix and sort of just like model how bias works. Yeah, so here's a concrete example that I tried to work out for the Bernstein bias example. So you can consider 0 to be like the space of Bernstein and 1 to be like Bernstein. And then let's say you have the cross operators like defined this way. This is a very simple example that is not necessarily like completely foolproof or anything. But yeah, let's say you have like three cross operators starting from index 0 all the way to 2. And yeah, you have one that's sort of biasing you towards Bernstein, and another one that's biasing you toward Bernstein. So one that's biasing you toward 1, and another one that's biasing you towards 0. That basically sort of shows you how bias can be modeled using these cross operators. So that's basically the idea that I have. But yeah, this does have limitations, which I will discuss. So this particular example, if you'll notice, is two-dimensional. So there's only so far that it can go. And it only assumes that you are like leaning completely towards something or completely against something. So as we saw here when I was like pointing out examples of the Mandela effect, we are sort of in the middle or we are confused when we see this information rather than strongly believing something. So yeah, that's a limitation of this model. And the channels that we have, the cross operators that we are defining, we are sort of choosing them instead of them just like naturally living there, which yeah, it's not that simple, generally speaking. And yeah, here meme and fact sort of act independently, if you notice. It's like two completely different cross operators. Whereas in reality, they may be like, as much as the status makes the way that the channel works could also be much more complex than that. So yeah, it doesn't show the full richness of how human memory works. So another thing that I wanted to talk about is we saw this phenomenon with the Pikachu example where your brain sort of like auto completes things. So a way to model that is we can consider recall to sort of be a measurement on a Hilbert space, in a sense that like a way to think about this is sort of, let's say you have what actually happened is what we remember is a subset of we. So that's sort of what a measurement is, because a measurement does sort of like lose information or bias you to it. Like it's just completely random what you remember. So the brain sort of like favors a schema consistent with sort of like the black tail tip thing. And yeah, so the formal shadow of this is that measurement is biased. And yeah, it could be biased, it's not always biased. But so in this case, the cross operator sort of gives higher weight. The cross operator should be defined in such a way that it gives higher weight toward the schema being complete than what is actually true. So yeah, so to summarize this entire like section on Mandela effect, that we have our like brain's belief system and the way that we remember things sort of biases, sort of like wants to say consistent with our worldview and the biases that we have. So we believe the version that is consistent with our worldview rather than what is real and what is true to what is given to us. So the next section that I have is on misinformation and how misinformation spread and why we believe misinformation um, to categorical models. So one of the most like famous examples of misinformation is that goldfish have like a 5 to 7 second memory, but this is in fact not true. And goldfishes do have a memory of like 3 months, which is not that great, but it's far more than 5 to 7 seconds. So yeah, that's sort of a strange thing that everyone believes because everyone just wants to like say something that's a fun fact that sounds cool, but it's not really true. And another myth is that human beings only use 10% of our brain, which is not true. In fact, we use like different sources of our brain every day. And I'm sure you've met some people who you think believes use 0% of their brains. So yeah, you never know. It's just like this is not true. This so to say the least. Um, so yeah, we often only like observe exactly what change happens to us or what our belief is after the operation happens. We don't really like notice the source. Most people don't notice the source of the information that they get, which is at least the oversimplification that I'm going to use for this example. Whereas the origin or context is sort of unseen. So C is sort of like it plays a role in changing your belief, but after that, it sort of like completely flies off of your head and you completely forget it. So that's one of the most common ways that misinformation is spread, and that is what I aim to model mathematically. So again, we go back to this notion of internal trace that I promised to talk more about before. So the internal trace, as defined by Koka and Abramsky, is that you have this max mixed trace and then this dagger one that sort of discards it. So you have something that takes you from the terminal object to actually having a belief and then completely forgetting the belief or like the source that you had for your memory. So the way to define the internal trace is basically this way. And the interesting thing about the way that internal trace is defined is that the final map that you get doesn't include C at all, but you're still able to go from A star tensor A to B star tensor B. Although C does play a role in the way that this map is defined, it's not actively playing a part in it in the final output, and it's sort of forgotten. So yeah, I just think
Because it particularly like dominates over,
what
no, like a particular like, kind of work for another, changes the.
no, like
system.
the C is sort of like pre-picked in a sense, because um yeah, it's pre-picked because you have like this internal trace notion, and yeah, C is picked. But then the way that the trace is defined, it sort of just like gets cancelled with its inverse or dual, I think, and then it just disappears. Yeah, I did the math to make sure that the trace is complete. I can show you that later on if you're interested. But yeah, so the map just ends up going from A star tensor A to B star tensor B, and C is just forgotten.
Is this like formally a trace in the sense of like we're defining a new monodal structure on CPM empty hill? Is this like, does this make it a trace monodal?
Yes.
Okay.
Yeah. So now you have this idea of purification. So this is again taken from Koch and Abramsky's work. So let's say you have a completely positive map F that goes from A star tensor A to B star tensor B. So there exists a C which G pure on A tensor C. So what purity really means here is that this trace definition that you have, you should be able to recover like under sort of morphism from it, like F such that F is equal to the trace of G. But the interesting thing is that this so-called purification process that you can do from the trace doesn't guarantee a unique G. There may be many different kinds of G that you can get from this trace process. So that means that there are many different, so what this means like more semantically is that there may be many different ways in which you can yield the same sort of information even from like different sorts of maybe even wrong sources. Um, and you completely like forget C. So yeah, that's sort of what we are trying to model here.
Is this trace over C the same thing as like the partial trace over C?
Yeah, but I think they defined it like specifically for completely positive maps. I personally am not aware of the general definition of an internal trace, so I don't know if it's the exact same. But
You need that.
yeah, but
I think
this
it's,
yeah.
I think,
Oh
but
yeah.
yes, I think.
Yeah, so we see this sort of indistinguishability problem where you're sort of like able to like recover this like random amount of G's from this trace definition, and the origins may be differed, but the observed update at the end from like A tensor A dual to B tensor B dual is going to be the same at the end, which means that there's lots of different hidden pipelines that just like and end up with you having the same belief push. So it sort of ends up happening that the reliable source and the unreliable source all get muddled up into the same thing, because someone may be believing the right thing, all despite getting it from a source that might be sort of sketchy. And it's sort of hard to tell what is reliable or what is unreliable these days. And that's basically what this is attempting to model.
If you go back to the definition of pure,
Yeah.
let's. G,
Oh, that's not a definition of pure. That's a definition that has the word pure in it.
Yeah.
What does the word pure
Not
mean
meaning
there?
this.
And pure here just means that you are basically able to get a morphism from this trace definition. Like whatever trace thing that you have, whatever morphism you get from that, it's just called pure for some reason, but I'm not sure what reason that is.
Yeah,
Yeah.
so we're saying that any a positive map. Is this a theorem or something? Are we saying that?
So like,
It's like I think it's stated as a lemma or definition or something in the paper that.
yeah. So,
I mean,
this is a bit, yeah, this.
But
Presumably,
the pure part is not like written as a definition. I know in like the quantum sense what purification basically means is sort of trying to make sense of a mixed state, I think. And yeah, when you like not measure, but when you I think it's measuring. When you're trying to like measure a mixed state, you may get like a lot of different results. I think that's what purification refers to, but I'm not sure. Please don't quote me on that.
and so he was saying G pure on A tensor C, we're saying it's a positive map from A tensor A star to, sorry, A tensor C times A tensor C star to B tensor C, B tensor C star.
Such that when you partial trace it,
Okay. And presumably that's like if I take C to be 1, they're always like I can just take F. I guess I'm not sure what this is like.
so yeah, maybe yeah. There's a cool story about how like this is to do with the fact that like something called like the church of the larger Hilbert state, which is that things aren't good, that you can make them look pure and bigger. So yeah, there's a lot of quantum
Okay,
computing
so
stuff
I guess I'm
around this.
confused by the
Yeah,
term pure, but maybe we can address that later.
Yeah,
or
sure.
something like that.
Yeah, sorry, I unfortunately have to throw a lot of information. I'm
Yeah,
not
yeah,
allowed to be
no,
able to do
yeah.
this. But yeah, perhaps this was not the greatest topic that I chose. But anyway, so we sort of there's this other thing that we don't get our information from one source. We may have many different sort of channels acting on us. So this is sort of just like a definition for the way that we can sum up different channels that come to us. And if there's like sort of this iteration that's happening, and like the thing is, if there's like a certain narrative that's like pushed by different sources of media, for example, that you consume, then maybe you may be biased to believe that something is true and not look at the other end. So that's sort of what this like aggregation and repetition process is sort of trying to model. So yeah, so this is just like the more psychological aspect of this. So this hidden register C is sort of just, it could be a platform or it could be like a person or a different framing or something that you saw in the news that sort of just like gets discarded, and it monitors the information loss that happens in the setting. And um the non-unique purification sort of shows you how origins are sort of indistinguishable at the end of the day. So yeah, you just get confused by what exactly the source is. And that's what C disappearing is supposed to model. So yeah, this is just a toy model that I came up with, definitely not perfect. But so let's say C has some context like a platform or a resell or something like that. And you pick this isometry V that goes from A to B tensor C, and you define G of O to be V row V dagger, and do this whole like trace definition on it. And G, by the definition of Koch and Abramsky, is supposed to be a pure completely positive map, if because it's like originating from the trace, if that is to be believed. And F is the observed completely positive map on the channel of beliefs. So different choices of V sort of can result to the exact same F. So yeah, that's what this is supposed to model. But yeah, again, this has a lot of limits because tracing out C sort of like you can't really recover exactly how the forgetting of C is happening because just like in quantum where you can't like exactly tell why the information loss is happening or why this like purification thing is indistinguishable, you sort of can't tell the same thing for human beliefs, which is a little bit not necessarily always true and not very general. But yeah, perhaps a remedy would be like to keep more registers that mean lots of different things and maybe compare how these registers are with each other. And yeah. So anyway, thus far I've been working in CPM FD but I wanted to expand to like more fusion category stuff. So that is what I will be talking about next. However, I'm quite bearish on the thinking that I've been doing for the conspiracy theory things, and I'm not 100% certain that this is going to lead to something, right? But rather, this is merely speculation from now on. Anyway, so these are some of my favorite conspiracy theories. Obviously, birds aren't real. If just before this talk, I was talking about how I saw a bird that I'm not convinced is real. So perhaps, yeah, this is a very American conspiracy theory, obviously. But
Birds are so wonderful. It's possible
yeah,
to believe
yeah.
that
They are, they are. No, but like there's so many people who still believe this, unironically. It's just kind of scary. Anyway, and there's under one that the moon landing is completely fake because the US flag is like waving and there's no wind on the moon, along with like a lot of different things. And there are in fact some politicians and some people who actually do like push for this and think that it is fake to this day. Which yeah, I find this very interesting to read
the real
about.
reason it's fake is the moon's fake.
Oh, that makes sense. Drew stole the moon like years ago.
Also standing in the car.
Yeah.
Anyway, and this is a lesser known, I think, conspiracy theory about chemtrails. But this is it. Yeah. At least I don't see it much on social media compared to other things, but I'm not sure. Yeah, so people think that these like white line thingies that like go off airplanes are basically just like ways for the government to track where the planes are going rather than actually being things. Rather than
It's the
Yep.
your brain.
oh that's
Yeah.
oh my god.
It's
Makes you what? No way. Oh, that's my favorite one. I bet. Anyway, so what do these conspiracy theories that we hear about have in common? These are stories that make sense. Like many times I've like watched these conspiracy theory videos and I think maybe this is true. And like most recently, me and a close friend slash instructor of mine, German, we spent 1 hour of his office time watching videos on the Denver airport and we were convinced that like it's satanic or something. But then the more you research like behind this, you understand that there's like an actual contradiction with whatever you've seen in the video. And like perhaps if you make the presuppositions that are made in the video and start listening using that, the story makes sense. But there's going to be some like something outside of the context that you're not considering that just makes everything fall apart. So, in a sense, these theories are very local and they're like confined to the information that you have at that point and don't like consider the entire global story. So, the way we do this when I was writing this, admittedly, I was thinking about braided fusion categories, but I don't think you necessarily need a fusion setting because I feel like this whole like semi-simple and rigid thing might be just too confined for what I'm really thinking about here. But let's say, for example, you have some category of fragments and the objects would be like different types of local information and the morphisms would be like different ways to connect them and connect information that is not the context. And the tensing would be a way to just have them together, like with the context that they share and braiding would be a way to just like consider the part that where like even if you swap the order of the updates, nothing really changes. So the goal is to basically form this locally coherent story that people will believe if you wanted to start your own conspiracy theory, for example. But where does this like really lie in the whole global scheme of things is really the question. So the braiding here sort of formalizes the order changes that would be harmless in a sense, or things that would be like isomorphic to each other if you change the order. And the hexagon and coherence laws sort of just like make sure that these swap sequences agree at least within the local framework that you're considering. So the intuition is that if like these updates that you have commute up to breeding, then they can coexist cleanly. So that's what allows us to like believe these conspiracy theories because they coexist in the world that assumes. So yeah, we'll basically test global coherence for these objects that sort of braid well. And for that, we use this thing called a Drinfeld or Murger center. I don't think those are the same things necessarily. Are they? A Drinfeld and Murger center is the same thing? No,
I don't fully on it.
they're not.
Sorry, what's it? Drinfeld and what?
I don't know what a Drinfeld is, but I'm pretty sure I meant Murger center here, not Drinfeld. So strike that. I do not mean Drinfeld, I mean Murger center. But because I know certainly the thing that I'm defining here is a Murger center, I don't know if it's a Drinfeld center. So scratch that, I mean Murger center. So Murger center is basically the part of the category where the blading sort of commutes completely. So X tensor Y is Y tensor X, and this like center part of the category is a subcategory of the full category. And yeah, this has like its own, like it satisfies coherence laws on its own and just can stay intact by itself. So what we say is that the objects of this category are called transparent because they completely commute with everything. And yeah, so the way you can model conspiracy theories is that perhaps they're like the Drinfeld center or this subcategory where everything sort of commutes and it makes sense together. But when you like consider it in the global context of the entire category, it does not make sense anymore. So yeah, the line of thinking that I have is maybe to at some point think about modeling conspiracy theories as Murger centers. So that's what I'm thinking about. Anyway, so I am going to summarize and talk about my future work, but before then, I have a very long acknowledgement section that I need to talk about. So I'll start with people who are here. Thank you, Tim, for coordinating my entire visit and for all of the fun discussions we've had about quantum related stuff. We haven't been able to talk a lot, but I'm very grateful for the little talking we've done. And I have decided my favorite quantum gate is the Toffoli gate.
That's it. It's great.
And Jason, thank you for answering my stupid questions about dots and teaching me everything I know today about coffee. I'm very glad to know that crema has nothing to do with milk. Pretty sure I would have embarrassed myself with this at some point. Jose, perhaps the most memorable conversation I've had with you is when we were walking back from the Holy Bush and you were talking about Brazilian wildlife. And then I decided if I'm ever going to Brazil, I will let Jose know. I will be sure to let you know if I have a trip to Brazil. Anyway, so for people who are not here, I'll start with Q. He has been a great friend. They have been a great friend to me, and I hope our paths will cross again. We have played so many video games together, and the last video game that we played was the Textorcist, and they were completely enraged by this game. Like it was a horrible game that I recommended for God knows what reason. David is not here, but we've had some nice conversations on quantum computation that I appreciated. Yeah, I don't do flattery, but I'm pretty confident that I'm the biggest fan of his work aged 20 and under at least. Anyway, Xiaoyan is not here either. I only got to talk to her for like a week, but we talked a lot about like modeling and computer science, which I know basically nothing about. And yeah, she told me a lot about the cool theoretical computer stuff, science stuff that she works with. But yeah, she's in Canada, and I hope our paths will cross again because somehow she's the closest to me from all of you, in distance at least. Anyway, so outside of this list, I would like to thank Brendan Fong for his consistent support to me in the last few months. I'm very grateful. And Brandon Shapiro, who worked for Topos, I guess, a few years ago. And he told me that Topos exists. So big thanks to Brandon. But yeah, all in all, I will miss all of you and eavesdropping many discussions on dots and cat cola, which I've learned a lot from, really, even though I've not been participating in them. But yeah, I struggled to like I've been struggling a lot with really just finding a mad community that I feel that I could be part of someday. But I feel like the category theory community and everyone at Topos just makes me feel like I can be a category theorist someday. But yeah, I'm glad. I hope our paths will cross again. But yeah, anyway, to just summarize that whatever I've been talking about here. So I talked about Mandela effects using these non-commuting channels and this category of completely positive maps and finite dimensional Hilbert spaces. Misinformation as this like multiple purification thing that you can do to mix states, and conspiracies as these like local fragments in bladed categories, so to the Murger Central. Yeah, future work that I want to is really just like flesh out the details of all of this at some point and maybe just like explore higher categorical lifts. Basically maybe use the extra structure that you get from two categories or bi categories or double categories or something to just like see if that can tell us more. And sort of these experiments that I've read about the last week, maybe just try to model them completely using math, which is very ambitious, but at some point that could be worth thinking about. And yeah, these toy models that I have are very annoying because they are just not realistic at all. So maybe just extend them to something that is more practical and makes more sense. But yeah, these are my references. That is the end. Thank you.
Okay, let's open Khyathi for her talk. Any questions?
Yeah, question slash suggestion would
Yep.
be like, I think it would be really interesting for you to look at some of the stuff that's going on with like, essentially like game theory type stuff. I think would be very interesting, like where they model belief in game theory, especially because there's a large overlap
The
between
what in game theory?
belief.
Oh, belief. Oh,
Like,
yeah.
I think there's a large overlap between people who do ZX stuff,
Oh,
people who like category theory, people who have students who now do game theory. There's like a nice little
Yeah.
community of like stuff there. So I think it might be interesting to see like what they're talking about, how they model belief, and like whether it's similar or like completely different. Or
Yeah, that would
there's
be
some cool
interesting.
things. I'll
Yeah.
point you towards some papers. That
That would be
great.
nice. Thank you.
Cool.
That seems close to what Q is doing as well, modeling
Yeah.
beliefs and
Oh
Oh,
yeah,
yeah.
different. I don't know. I don't know anything about
enriched
what.
categories.
Yeah. Jesus. Yeah.
Other questions? I think I have some like technical maths questions
Okay,
about like
well.
QO maps and but maybe I'll save those for later.
Have them over coffee and
Yeah. So just about the last thing we were talking about in the conspiracy theory,
Oh, yeah.
theory section. So are you actually looking at like braided categories or just monoidal categories where these certain objects come with these braiding
So
mechanisms?
I think I want to look at braided categories because I think braided categories are the only ones that have a Murger Central. So basically just have like a braided whole category and then consider the Murger Central part of it, which is where everything commutes.
I'm just wondering, because like
Yeah.
in a braided category, won't you always get these?
Oh, no, that's like the identity here, not just an isomorphism, I think.
Where x tends to y to y tends to x is natural.
Yeah, so like the part that completely commutes, not the part that's just like like x tensor y is isomorphic to y tensor x, not that part, just the part where it's the identity.
So it's like gamma's not just an arbitrary morphism. It's an iso. Or
Sure,
Yeah.
but that's
or an
true for
equal,
braiding, right?
or an equal something. Yeah.
Yeah, equality, yeah, that's what I'm trying to say.
It's an id.
It's an identity.
Yeah.
These are strictly okay. Okay. Okay.
Yeah, that's.
I mean, there is a, I
That's
guess
what I mean.
you could weaken the notion of braiding so that all of these maps have a non-invertible commutator and then look at the ones where it's invertible or something. Or
That would be interesting.
I
Yeah,
don't know.
maybe.
Anyway, just curious about that. Okay, any other questions? No, if not, let's think Khyathi again.